All right, probability. Let's jump into it. Make sure you do put your name, today's date, and your class period. And don't worry about homework, obviously. Okay, and then for the summary, once you finish these notes, you need to go back up to the summary section and give your summary. And then that's what you're going to do before you turn these in. All right. So let's start with the first main idea, which is probability. And before we continue, here are some essential questions that you need to keep in mind. What is the counting principle? That's right down here, so keep an eye out for that. How do I draw a sample space or a tree diagram? We'll do that there. And how do I find the probability of an event? That'll be further down in the notes. That's probability. It's a numerical value from 0 to 1. Okay, if you're talking about fraction or decimal form, but if you're talking about percent form, it'll be from 0% to 100%. Okay, so just be aware of that. That measures the likelihood of an event happening. So basically, how likely is it going to occur? Probability can be given as, again, a fraction, decimal, or percent. All right, the set of all possible outcomes in a situation is what the sample space is. So this is sample space, and we're going to use a tree diagram to figure out what the sample space is. Example number 1 just says that a quarter is flipped twice. The quarter can land on either heads or tails. Represent the sample space as an organized list and a tree diagram. So when you flip a coin, and we're doing this 2 times, so we have the first flip. So for the first flip, you can either choose head, or can either land on heads or tails. And then for the second flip, if I land on heads the first time, I can land on heads again, or I can land on tails. So I could have heads first, then heads second, or I can have heads first, then tails second. Same thing if you flip a tails first. You can flip tails first and heads second, or you can flip tails first and tails second. So there you go. That's a tree diagram. And now we're going to make an organized list. Ooh. So just to reiterate, we could have heads first and then tails. Heads first and then heads again. We could have heads first and then tails. We could have tails first and then heads. I'm just switching back and forth here. We could have tails first and then tails again. And those are the only possible outcomes. Take a minute. Think about it. Can you think of any other ways to do this? Can you think of any more combinations we can add? I hope the answer is no. All right, so this is the sample space. And it's in list form. And if you look, there are 4 possible outcomes. Alrighty, fundamental counting principle is next. The number of possible outcomes in a sample space can also be found by multiplying the number of possible outcomes from each stage or event. In other words, if there are X ways of doing one thing and Y ways to doing another, then there are X times Y ways of doing both. For example, a woman has 3 children, and for the sake of this problem, we're going to be in a binary situation. How many different possible outcomes are there for the gender, sex, of her 3 children? Use the fundamental counting principle to calculate the possible outcomes. Then draw the sample space to check your work. All right, so again, for the sake of this problem, we're going to keep it real simple with just 2 sexes for the child. So we have the first kiddo, we have the second kiddo, and we have the third kiddo. So the first kiddo can come out as male or female. Okay, and that would be 2 possible outcomes. The second kiddo could come out as male or female. So if your first kid is male, your second kid could be male. If your first kid is male, your second kid could be female. Same thing over here. Your first kid could be female, then you can have a male. Your first kid could be female, then your second could also be female. All right, and then for the third option here, we have your first child could be male, your second child could be male, your third child could be male. Your first and second could be male, and your third could be a female. And then you could have male, female, male, or you could have male, female, female, okay? All right, so if you start off with a female kid, you could have female first, male second, then another male for third. You could have female first, male second, then last kid could be a female. You could have female first, female second, and then a male kid last. And then you could have female, female, female. So 3 female kids. Did I say student? I meant kid. I don't know. Anywho, so those are the possible outcomes for this particular problem. So if I were to list these, I'm going to list them kind of fast. All right, cool. There we go. So those are your options. If you can think of another option, please try right now. Okay, you can't. So that would be the sample space for this particular problem. Scooch this over. Okay. And this is the sample space. And then this time there are 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. So 8 possible outcomes. Also, okay, so that was like the long way. I'm so sorry. I did this the long way. Now, for the fundamental counting principle, they're basically saying, hey, there's a shortcut to figuring out how many possible outcomes there are. What, you ask? By multiplying. So I'm going to do this over here. So we got the first, second, and third event, which in this case would be churn. So I'll just keep it black or gray, whatever. So for the first kid, we have 2 options. For the second kid, we have 2 options. For the third kid, we have 2 options. All right, and then you just multiply those, and then you get 8 possible outcomes. All right, so the sample space is 8 possible outcomes. Now, if you multiply it, it doesn't tell you all the different outcomes. You have to figure that out, but it at least tells you how many there are. So, yeah. All right. So, Ed, if this problem bothers you, just think about it like coins. All right, we're moving right along. Experimental probability. All right, so experimental. Think experiment. Something is actually happening. It's not like a theory. It's not like made up in your head. It's actually happening, or it already happened. Experimental probability is the ratio of the number of times an event actually occurs to the number of times the experiment is done. Okay, so basically, how many times did it happen? Like, how many times did the thing you're looking for happen versus, like, the total number of things? Okay, yeah, okay. So I'll just put total down here in parentheses. Total always goes at the bottom. All right, so for example 3, a quality control inspector samples 500 LCD monitors and finds a defect in 3 of them. All right, what is the experimental probability that a monitor selected at random will have a defect? So we need the probability of defective monitors. So I'll put P defect. That literally translates to the probability of a defect. Equals 3, so there were 3 defective monitors out of 500 total monitors. All right, you can leave your answer just like that. That would be the fraction form. If you have to or want to change it to a decimal, you simply do numerator divided by denominator, and that would be 0.006, I believe. And then if you want to change it to a percent, then you just multiply by 100, and then that would be 0.6%. It's okay if your percent has a decimal in it. That does not make it a decimal. That's not in decimal form. It's just a percent. That's not a full percent. All right. If the company manufactures 15,240 monitors in a month, how many are likely to have a defect based on the quality inspector's results? So this is a little different. This is like, okay, based on the experiment that happened, can we make a prediction? So when that happens, this is what you need to do. You're going to have the, Sorry, trying to make this make sense. All right, so we're going to have the number of events over the total. So that's basically what this thing up here said, right? I'm just simplifying it. And then that's going to equal the predicted number of events, right? Because we're trying to predict over, sorry about that, over the new total. Okay, so when it's asking you to predict, when it's asking you to predict the future based on an experiment that already happened, then you need to use this proportion. Good gravy. Just forgot that whole word. Let's do it. All right, so the number of events over the total, that's 3 over 500, right? Because 3 were defective, 500 total. Now, the new total is 15,240, and we don't know what the predicted number is yet. You can put an X right there if you like. All right, and then you're going to use what math teachers everywhere hate the name of. It's called the butterfly method. That sentence was terrible. I'm so sorry. Or you can just call it cross multiplying. Anyway, so 3 times 15,240. So 3 times 15,240. And that's 45,720. So 45,720. And then you're just going to divide it by that 500. Okay. I'm going to do this the nice, pretty algebra way, but you can just divide. You don't have to show all this. All right, and you divide both sides by 500. This is the nice, pretty algebra way. The shortcut is just to multiply and then divide. Make it simple. All right, and so we get x equals, I think it's like 91 point something. Yeah, 91.44. I did it up there. So 45720, I'll do it again. Divided by 500 is, oh, shucky ducky. 45720 divided by 500 with a decimal, and then we change it to decimal form, 91.44. So 91.44. Now, the question is asking like a real world situation, so you can't have like a part of a monitor. So you have to give a whole number answer. So I would say like 91. Okay. Theoretical probability. Okay, so we just talked about experimental. Now we're going to talk about theoretical. Experimental is when it actually happened. Theoretical is when it hasn't happened. We're just saying based on how it looks, this is what we think might happen. All right, so the ratio of the number of ways an event occurs to the number of possible outcomes. Possible. Okay, so basically favorable outcomes over total, okay? Favorable outcomes over, I'll write it down. It's the same thing as saying favorable outcomes over total. Okay, that's what this is saying basically. All right, so example 2. 2 dice are rolled, draw the sample space and answer the following question. Okay, so here's what I want you to write down. We're talking about regular 6-sided dice. So that's a 6-sided die. Each die has like, a number on it. And of course the numbers are just dots, but we're going to use numbers instead of dots. 4, 5, 6. Okay. Let me make myself abundantly clear as to what I'm saying. Can I do that? Can I do that? 2, 3, 4, 5, 6. So you have like 1, 2, 3, 4, 5, 6. Okay, that's what I'm saying. So this is 1, this is 2, this is 3, this is 4, this is 5. This is, okay, that's what I'm saying. It says there are 2 of them. Okay. All right, moving right along here. So for the first die, I'm going to call it the purple one. You could roll a 1 first. So this whole column is 1s. This whole column is 2s. You could roll a 2 first. You could roll a 3 first. And so on and so forth. Okay, now you can roll a 1 first and a 1 second, a 1 first and a 2, then a 1 first and a 3. You can roll a 1 first and then roll a 4 second. You can roll a 1 first and a 5 second. You can roll a 1 first and you can roll a 6 on the second. Ta-da! Okay, so these are all possibilities. Now, I wrote these in 2 different colors so you wouldn't think that I'm writing like numbers. like single numbers like 11, 21, 31, 41, 51. No, this is a 1 and a 1, a 2 and a 1, a 3 and a 1, a 4 and a 1. So pretend there's a comma in between. I don't feel like making a bunch of commas. All right, what's the probability that you roll a 2 and a 3? So let's see how many of those we've got. So what's the probability? A 2 and a 3 at the same time. So we got a 2 and a 3 right here, and then a 2 and a 3 right there. It's in a different order, but it didn't tell us a specific order, so we good. So that was 2 possible ways we could roll a 3 and a 2. And how many are there total? Well, it's 6 by 6, which is 36. Okay, if you don't believe me, look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Okay? Gosh. All right, we're going to simplify this fraction to 1 over 18. You can leave it in fraction form. However, if it's a test and it's like a griddable, or if it's multiple choice, make sure you change it to a decimal by doing the top. I don't trust y'all. The top divided by the bottom. So 1 divided by 18, and that would be, oops. Okay, that would, dang it, Bobby. Okay, that would be 0.06 or 0.05 repeating. So it could be 0.05 repeating, or you can just leave it like this. Okay, or if you want to change it to a percent, you could change it to the percent, 5.5 repeating percent. Okay, so you got options. Okay, you got the fraction, you got the decimal, and then you got the percent. So you can choose on a worksheet. I'm going to keep it as a fraction because I don't feel like doing all that extra work. All right, what's the probability that you roll a double? So let's go ahead and take a look. It's in a book. Reading Rainbow. All right, double. So we got a double here, double here, double here, double, double, double. 6 doubles. 6 possible doubles out of 36 possible outcomes. And then if we simplify that, that's just 1/6, okay? Probability that you roll a sum of 7. All right, let me get rid of all this. All right, a sum of 7. Sum means you add it up and it equals 7. 1 plus 6 is 7. 2 plus 5 is 7. 3 plus 4 is 7. 4 plus 3 is 7. 5 plus 2 is 7. And 6 plus 1 is 7. How many possible ways can we get 7? 6 different ways. How many possible outcomes are there? 36. It's the same old, same old. And look. To simplify this, just, you could be like, oh, I could divide both these by 6. Ooh. 6 divided by 6 is 1. 36 divided by 6 is 6. Okay, you can do it like that. Or if you don't like that, you can just come over here, type it in your calculator, hit enter. That's it, baby. Just hit enter and it's going to simplify it for you because technology. All right, moving right along here. The probability that you roll a 4 or a 5. All right, so let's come back up here. Okay. 4 or a 5. It doesn't have to be 4 and a 5 at the same time. You can roll a 4 or a 5. So I see that we got some 4s here. Boom, this whole column is full of 4s. We got some 5s here. Boom, that whole column is full of 5s. Now let's look the other way. We could roll a 4 on the second die, or a 5 on the second. So these are all the different boxes that have a 4 or a 5 in it. Let's count them up. Let me use this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 out of 36 possible outcomes. Total possible outcomes. All right, and then we could just simplify that. I'm going to come over here and show y'all how to do it on the calculator again. Just 20 divided by 36. Boom. 5 out of 9 does it for you. All right. Or you can just divide the top and the bottom by 4. So you can just do like divided by 4, divided by 4. You still get 5 over 9. Anywho, there you go. Your fractions have to be in simplest form, okay? Don't be lazy. I'm already making you lazy enough. All right, what's the probability that one of the die will land on a number less than 4? All right, so let's look at the numbers less than 4. So I see here we got all of these numbers. This is all less than 4. And I'm saying that there is a number less than 4. It says one of the die will land on a number less than 4. So all of these that I highlighted have at least one number that's less than 4. And then same thing this way. All of these have a number less than 4. The rest of them only have numbers 4 and greater. And again, only one of them has to be less than 4. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 21, 22, 45, 67. So 27. And then again, 36 total. All right, if we divide both of those by 9, or you can type it in your calculator if you couldn't think of that, that'd be 3 over 4. All right, cool. So that's that. Theoretical probability in a nutshell. Moving on to complement. This one's real simple. It sounds complicated, but it's really not. Probability of a complement is the ratio. The sum of the probability of an event. Yeah. Happening. All right, so anyways, the sum of the probability of an event happening in its complement is 1. Okay, so basically, the probability of the thing happening plus the probability that it won't happen is going to equal 100%. Okay, and I'll put or 100%. All right, so likewise, the probability of the thing not happening equals 1 minus the probability of it happening. Or again, this could be 100% if you're using percent. Okay, so for this problem, we have 10 marbles, 10 red marbles. Always write down your total first. 8 green, 5 blue, 6 white. And then what's the probability of randomly selecting a marble that is not green? So we want the probability of not green, which according to this is going to equal 1 minus the probability of green. You feel me? You heard me? So anyways, let's go ahead and add this up. We got 10 plus 8 plus 5 plus 6. So you can just add it up over here. Get 29. All right, so the total is 29. All right, so the probability of not green is going to equal 1 minus the probability of green. Well, how many greens are there? 8. And then the total is 29. So 1 minus 8 out of 29 will give us our answer. 1 minus 8 out of 29. Hit enter. 21 over 29. And that equals 21 over 29. And that's it. If you want to change it to a decimal or a percent, my bad, be my guest.